Good day everyone and welcome to this video lesson. Do you wonder how to graph a piecewise function in GeoGebra? Or are you curious about illustrating the interval of a function in GeoGebra? And have you thought about how to illustrate the limit of a function and identify points of discontinuity? If yes, please join me in this video lesson. Please pause the video to read the following learning objectives. At the end of this video lesson, the student or a teacher would know the following GeoGebra syntaxes for graphing a piecewise function in GeoGebra, illustrating the interval of a piecewise function, and calculating the limit from above or below of any function. Be able to illustrate the semi-manual calculations of the limit and illustrate on the graph the visual representation of the limits and the x values where the discontinuity lies. Also, the student and teacher would be able to determine algebraically using basic calculus theorems the discontinuity or continuity of a piecewise function on an interval. And lastly, as effective objectives, the student and teacher would be able to appreciate the noble and classical beginnings of the discovery of limits as an operation to visualize the behavior of functions, considering the absence of graphical visualization tools like GeoGebra long time ago. We would be able to appreciate the application of limits in the creation of these tools like GeoGebra, and we would be able to gain confidence in using GeoGebra and other tools to analyze and illustrate functions, recognizing their value in enhancing understanding and communication of mathematical concepts. Consider the function below. Determine if f of x is continuous on the interval -2, 5. The function is a piecewise function with 3 pairs of conditions and expressions. If x is greater than 1, the expression is square root of x minus 1. And then if x is equal to 1, we are going to have constant function 3. And if x is less than 1, then we're going to use the expression for negative x squared. Our task is to demonstrate algebraically using basic calculus theorems whether such a piecewise function is continuous or discontinuous on the interval -2, 5. So step number 1, check the domain, the interval, for any undefined values of y or f of x not element of the real number system. To determine continuity of an interval, we need to ensure that every input x within the interval produces a corresponding output y or a function value f of x that is a real number. If any input x results in an output y that is not a real number, then automatically the function is discontinuous. Why? Because by definition, if there exists any x in the interval where f of x is not a real number, such as undefined values, infinite values, or non-real complex numbers, then the function f of x is considered discontinuous at that point. Therefore, the statement correctly captures the essence of continuity and discontinuity of functions on intervals in calculus. We will now create a table of x and y values and complete it. So please pay attention to the algebra part, which involves the substitution process. So we replace the variable x with its assigned value and follow the order operations of PEMDAS. So please feel free to follow along and perform the same process at your desk. So if our x value is -1, then that would be x less than 1. So the expression we're going to use is for negative x squared. And here's the substitution process. So if x is negative 1, then the y value is 3. Now, if the x value is 1, automatically the value is also 3. And if the x value is 0, we substitute 0 to the polynomial for negative x squared. The y value is 4. Please continue to observe the substitution process and the completion of the table of x and y values. So if x is 2, y is 1. If x is 3, then y is approximately equal to 1.14. If x is 4, the y value is 1.732. And if the x is 5, the y value is 2. Please take note that at this part, we are having x values greater than 1. So the condition is x greater than 1. So the expression to use is square root of x minus 1. So again, I hope that you have able to observe the substitution process and the completion of the table of x and y values. Enjoy the gift of humanity's creativity. Let's use GeoGebra as a tool to visualize the piecewise function. Let's use GeoGebra as a tangible application of limits as an operation. Note, the graph that we will produce will not exist without the foundation and concepts of limits as an operation. So how to enter a piecewise function in GeoGebra? Alright, so the syntax is governed by the if-then-else conditional statements. The syntax will be f of x is equal to if condition 1, comma, expression 1, comma, if, then condition 2, comma, expression 2, and expression 3. So first, we're going to write the condition inside the first parenthesis, right? The first condition. Then write the expression for when the condition is true, then followed by a comma. Next, write another if statement for when the first condition is false. This includes another condition followed by a comma. Then write the expression for when the second condition is true, so that's expression number 2, followed by a comma. And finally, write the expression for when both the conditions are false. So please observe as I type this syntax in GeoGebra. Alright, so dear class, here is now the graph of the piecewise function. So we can change the color of this graph. If you like already the purple, then you can just change the thickness to make it more visible. How to show the interval of the piecewise function? So it's simple. So after writing the piecewise function, then type function and then call the piecewise function, so that's f of x, then comma, then the next element or component will be the left boundary of the interval as the start value, so that would be -2, comma, and then the last component will be the right boundary of the interval as the end value, so that would be 5. By default, this syntax will consider closed boundaries. So please edit the inequality for an open interval. So in this case, our left boundary is an open interval -2. So we're going to change this instead of x greater equal to -2, it will just be greater than -2. Again, we can change the color and style of the interval. So just like this. So click here, then settings, and then let's make use of green for example, and then increase the thickness. Alright, so this is the green one. The green curve here is now the interval, the curve on the interval. As you can see, tracing the green curve, we really cannot complete it from start to finish without lifting our pencil, right? Indicating that the function is discontinuous in this interval. So let's continue to show such discontinuity algebraically using basic calculus theorems. So please watch the second video so we can enjoy some algebra and some basic calculus theorems. Thank you again for watching.